Hey guys, so obviously I'm not here today. I'm going to give you, we're going to start Taylor series and Maclaurin series, which is an extension of the power series stuff we've been doing. I've broken it up I've left out some of the trickier parts to do when I get back. And we're just going to fill in this note, which I'm actually going to post for you on Haiku together, and I'll get you to try some homework questions. So, we are going to look at power series now. Power series as functions. We can think of, say if we take a power series like this, and really this is, I didn't put the bounds, this is a sum from n equals 1 to infinity of x to the n over n squared. Well, I can think this is a function of x, like I'm allowed to plug in x values. And some values, it will actually make sense because the series will converge. For instance, in this function, f of 1 is the sum of n equals 1 to infinity of 1 to the n over n squared, which is 1 over n squared, which is a convergent series. So I can plug in 1, and I get a y value. I get whatever this actually converges to. I don't know what it converges to, but I do know it converges. So when I plug in 1 for x, I actually get a y value out of it. This is a function. I get one y value. But I can plug in a half, and I'll get this series, and that actually converges as well. You can use a convergence test on this that we did in the last unit. But some things I can't plug in, like I can't plug 2 into this. F of 2 is 2 to the n over n squared, and that's actually a divergent series. So power series can be functions, and their domain is their interval of convergence, which we did last unit. And okay, well, why care? Who cares? Like, I don't know. Let's explore some reasons why we might find this interesting. And before we go on, just know that we can actually differentiate these series term by term. So let's do even a really easy series. If I have f of x is x plus x squared plus x cubed, blah, 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 its derivative, I can actually, where it's on its interval of convergence, its derivative is the term by term derivative. That's actually pretty cool. I can just differentiate each term. I get another power series that is its derivative, but this only holds on the interval of convergence of the original series. And now there's one very, very, very special type of power series. It's called a Maclaurin series, and when I get back, we're actually going to look at its more general kind of big brother called the Taylor series. But really all you need to know you can find in Maclaurin series. And we take some function we know, f of x. Maybe it's sine x, maybe it's tan x, maybe it's e to the x. Some function we know, and a function that we can differentiate. And we can make a series out of f. What do we do? Well, the first term we call f of 0. The second term is f prime of 0 divided by 1 factorial times x to the power 1. And then the next term is f double prime at 0 divided by 2 factorial times x squared. See, this is a power series. We have powers of x, and the coefficients in front of each power of x we get from our original function. And you can use a sigma notation. This is a formula for the Maclaurin series of f. So as of right now, this Maclaurin series is just some random series we can create by plugging values in to f to get the coefficients. And this function exists whenever the kth derivative exists. Okay, so this is weird. Let's do an example. Maybe that will help. Let's look at e to the x. Let's get its Maclaurin series. Okay, well, f of 0 is e to the 0, which is 1. The nice thing is all the derivatives of e to the x are e to the x. This is also 1. F double prime of 0 is 1. Okay, so, and this will keep going. So the Maclaurin series is f, so let's add these f, let's just do it at f of 0 plus f prime of 0 over 1 factorial plus f double prime of 0 over 2 factorial plus, let's do one more, f triple prime of 0 over 3 factorial, and that equals, let's see, 1 plus, x squared, x cubed. This equals this plus x plus f double prime 0 is 1, x squared over 2 factorial plus x cubed over 3 factorial. And if you wanted to get fancy, you could do a sigma notation. This is the sum of 0 to infinity of x to the n over n factorial. And that is the Maclaurin series of e to the x. And here is an amazing fact. Okay, an amazing fact. On its radius of convergence. So whenever this series here converges, it actually equals e to the x at that value. So what does that mean? If I had e to the 1/2, well, that's actually the sum, 0 to infinity of 1/2 to the n over, I'm plugging in 1/2. And okay, well, that's 1/2 to the 0 over 0 factorial plus 1/2 to the 1 over 1 factorial plus 1/2 to, these are equal. And of course I can never actually add up all infinity terms of the series, but I can get a really close approximation if I take, say, 5 terms or 7 terms or 100 terms. It is just amazing that these are completely equal. And now we'd have to look at the radius of convergence of the series, all that. But we're going to worry about that another day. Okay, so maybe let's do one more Maclaurin series. Let's do sine of x. Okay, let's do sine of x is equal to f of x. Well, f of 0 is, sine of 0 is 0. F prime of 0 is cosine of 0, which is 1. F double prime of 0, derivative of cosine is negative sine, and that is 0. F triple prime of 0 is negative cosine of 0, which is negative 1. Now let's keep going until we really get a good handle on this pattern. F to the 4 of 0 is the derivative of negative cos, which is sine 0. F to the 5. And we see we've gotten back. Like we're cycling at this point. We've done cos. Then after cos, we know we get negative sine, cos 1. So really we get 0, 1, 0, negative 1, 0, 1, blah, 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 blah. So what does our Maclaurin series, I'm going to write equals because these are equal wherever they converge, these series. Well, it's equal to f of 0 is 0 over 0 factorial. Sorry, I'm losing something here. Plus, all right, f prime of 0 is 1 over 1 factorial x plus 0 over 2 factorial x squared plus, let's see, f triple prime negative 1. So I'm going to call this negative 1 over 3 factorial x cubed plus 0x to the 4 over 4 factorial. And then by the time we get to 5, it's plus x to the 5 over 5 factorial plus blah, 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 blah. So let's simplify. This is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. And you'll see this is an alternating series. And if you kept going, you get all the odd powers of x only. So really, if you wanted to be nice and fancy, 1 to infinity of x to the 2n minus 1 over 2n minus 1 factorial. That should work. And this is, we forgot our -1. We want to start positive, so we have to do n minus 1. But this will suffice, writing it like this. And all of these ones I've asked you to do in your example, e to the x, sine of x, cos of x, and ln of 1 plus x, those are all in your formula booklet for you to use freely. So I'll leave it up to you to do cos of x, or like cos of x, ln of 1 plus x on your own. But they are in your formula booklet. So why don't you try pages 4 to 5 in chapter 30 of the option book and do numbers 1 to 7. There's some interesting questions in there, and it's really just using your this formula right here, that if you have some function f, its Maclaurin series is given by this formula. For now, just think of it as a formula that you use to generate a power series from a known function that you know how to differentiate, and accept that on its radius of convergence, the Maclaurin series that we are going to be dealing with actually converge to the function. And note that for sure the ones we're going to talk about, for instance, e to the x, sine of x, cos of x, and ln of 1 plus x, they converge for all the x values in their domain. Sorry, quick correction to what I just said. E to the x, sine of x, and cosine of x, those three, they converge for every x value. Ln of 1 plus x, that actually we'll see later, it converges for this this domain, this interval of convergence. But for now, you can take those as fact, and their Maclaurin series are in your formula booklet.